So we are technically going to continue on from last time, and that summary is going to be very useful, but it has been a while since we graphed, so let's go back and actually graph f of x equals 2 to the x, the parent function, first, and then we can do these transformations. All right, so just recall, anything to the 0 power is 1, 2 to the first is 2, 2 to the second is 4, and then negative exponents are fractions. So that means 1 over 2 and 1 over 4. Okay, so plot those. Start with the y-intercept, and 2 to the first, 2 to the second, and 2 to the third even. That will fit, so let's put that on there as well, 8. And then we have half and a fourth, and that should be good enough. I'm just going to dot this. Like so. All right, now let's do these transformations and use your paper that you have. Remind yourself, what does this negative do to the graph? What is that 2 to the negative x? How is that related to 2 to the positive x? What changes? And then everybody says all at once. It's exactly reflection, y-axis. All right, so over here, graphically, we can just reflect each of these. The y-intercept stays put, but everything else will reflect. So we shouldn't really have to fill out the table to answer this. And really, you want to be thinking about what happens in the long run as far as x gets increasingly big or increasingly small. What does y approach? You want to know that as well. And if we absolutely need to, yes, we can get these answers. Now, we just basically flip-flop the x's, the positive and negative x's, right? Because that's what this means. Negative x is the opposite of x. So it turns out all these are the opposite. What was positive 2 answer is now negative 2 answer. So since x originally was 4, this is going to be 4 up here, right? And then 2, 2, and then 1. Because the y-intercept did not change. Now the positive exponents are now the fractions. 1/2 and 1/3. No, 1/4. There we go. And then we can do this one more time. So looking at your paper right there, what does that 2 do to the graph? And this is going to be a little new. What does that 2 do? Find it on your chart. I'm hearing it. Horizontal. All right. And the factor is what? It's not 2. It's 1/2. So it's 1 over that number, right? For the horizontal. So what does that mean graphically? So you see how far it is from the y-axis, and you go the factor's distance. So for this one, it says it's only half the distance. So for instance, you just find the midpoint for all of them between the axis and the original point. Just find the midpoint. It's halfway there. Halfway there. Oh no. It should be here. 2 to the 3rd, yeah. And then we can graph those. Oh no. Halfway there and halfway there. So you want to know how these various transformations affect the graph with or without numbers. So sometimes they just put empty axis with no numbers, and instead of saying 2 to something, they might say, well, how is a to the x and a to the negative 2x related? And you don't have any way of plugging in numbers and checking. And all you have to say is, well, it's going to be a reflection over the y-axis, and it's going to have a horizontal dilation of 1/2, right? So the number of the base isn't important. It's just knowing what these things do individually. And yes, you do have to memorize it. Can't have that chart on a test. can't have that chart during AP test either, right? So we have to get used to the idea of memorizing things. But here we do actually have it, so we could go through and just take these, and we're going to raise it or square it, so that would turn into 16. That's why we're not able to graph -2, because it goes off the graph. And then we also have 4 and 1, and then squaring 1/2 is 1/4. Squaring 1/4 is 1/16. All right. And then it asks below, describe the transformation of the y-intercept from the parent graph for f of x to g of x to h of x. Well, they're all the same. They all went through the same y-intercept. Because for all of these, we could rewrite them in that format. Okay, so all y-intercepts are the same. Now we start doing translations where we slide left, right, up, and down. The y-intercepts do change, but without those, pluses and minuses everywhere, if we don't have any pluses or minuses, just a negative, that y-intercept stays put. All right. So that was a horizontal dilation. Okay. Oh, be careful, it is dilation. Okay, dilation, not dilation, like diagram. It's just dilation, di, and then lation. Sometimes people spell that wrong. All right, let's try another. This time the negative is in front. So going back to your sheet, what does this negative in front do to the graph? And we could put up our parent function again. Y equals 2 to the x if you want. That helps. Hopefully we just keep on doing this and you get so used to it you can graph this in your sleep. Okay, so we got that. So what does this negative do to the graph according to your cheat sheet? And everybody says at the same time? With enthusiasm, I like it. So that's a reflection across the y-axis. Yeah. So we take each one of these and that's what I said. X-axis. Yes. Thank you. Here we go. Here we go. Here we go. Yeah, so no table necessary, right? We don't have the table anymore like the last ones. So we don't need it. We're doing this geometrically. Okay, so connect all those to each other. All right. Then lastly, we have one more part to that, so that's going to be g of x. Oh, actually, does it say? Oh, label. We should label, like it says in part A. Label the y-intercept, so that would be right here. About 0, -1. And it's also labeled the function f of x. And then we can graph g of x. So it's just f of x plus 3. All right, so what does the plus 3 do to the graph? Does that move it left, right, or up and down? Up. Yeah, so that's either shift or translation. Up 3. So take each one of those from the second graph here and just move it up 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Half, quarter. There we go. And does say to label it, so follow the direction. So we got our y-intercept at 0, -2, no, +2. And this is g of x. There we go. And for all these, we want to be thinking about limits. Remember those? We haven't done those, talked about those in a while, but we have our negative infinity and our positive infinity. So we could, for each one of these, we can ask, well, what is the limit, let's say, of g of x as x approaches negative infinity? Remember, this just means as we go left on the graph. That's all that means. So where's this graph going? What's the y value is getting closest to? And we can say, well, it's that asymptote, right? It's just getting close to 3. And then same thing over here. We can say, what is the limit as the x goes to positive infinity? That just means as we go right on the graph. What is the y? What are the y values doing? They're going down, down, down forever, negative infinity. And then if we do a reflection across the y-axis, these would switch. So just be thinking about that as well. Like, how does doing a reflection or a translation or a stretch change what's going on at the end behavior? Usually, it only changes really when you are doing a reflection, or if your asymptote might change if you shift up, something like that. Okay. All right, so let's keep going. And these both had, what, 2 as the base. So what happens if we have a fraction as the base? That's the next thing. Basically, it is, well, rewrite it without it being a fraction. So 1/3, as you know, is the same as 3 to the -1 power. So we rewrite 1/3 to the x as 3 to the -1 to the x. And through exponent rules, you just multiply those, and you get 3 to the -x, which is good because we know that this is a reflection across the y-axis. Right? So like the whole purpose for doing this is realizing if you know what 3 to the x looks like, 1/3 to the x is a reflection across the y-axis. So that's why we rewrite it this way. So instead of, we're going to start at 1 here, of course, but it's going to be a reflection. So normally I'd say 3 to the 1 is 3. Well, now it's going to be 3 to the -1 is 3. And 3 to the -2 is 9. Okay? And of course, so it's going to be concave up, going down, decreasing, like so. Now, if you need to, of course, you could draw the parent function if you needed to, if that's easier. But it's almost easier to do the parent function mentally and say, well, it'd normally be here, and then just reflect it over. And then 3 squared would be at 9, and then just reflect it over without having to actually draw the parent graph. Okay, so that is f of x right here. That's f of x. Now we have a g of x, which says do these things. So what does the x minus 4 here, and what does the plus 2 here do to the graph? Right 4 and up 2. So just take each of those points. Right 4, 1, 2, 3, 4, up 2. 1, 2, 3, 4, up 2. And we got 1, 2, 3, 4, up 2. And of course, this one will take us off. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, up 2 would be somewhere around here. You don't want to actually graph up to it, but you can use to aim. So we'll stop the graph at the top. But just imagine if it did keep going, that's where it would connect. And our asymptote did move up too because of that right here. So that plus or minus on the end changes where the asymptote is. And it just asks, describe the transformation from G to F, or from F to G. So from F to G, it's really just this right here, just write it out though. The graph is translated forward to the right or shifted forward to the right and up 2. So you can write that in and however you want. Your choice. I had someone ask me if it's okay to do this whole coordinate method. So this is called the mapping. You could say something like this. You want to be so that from f of x to g of x, the coordinates were, here's the mapping for the coordinates or something like that. All right, so almost there. So this is the whole purpose of this was this technique of if you have a fraction base, let's change it to a negative so we could do some reflecting. So same thing here for number 9. We have, once again, a fraction base, so let's change that. Right? Instead of 1 over 3, it's now 1 over 2, so very similar. So we have y equals, and let's just break these apart, because each of these does a different thing. We got a negative, got a 1/2, and I'm going to write the base instead of 1/2 is going to be 2. So this now becomes negative x, just like the prior example. And it says to describe the transformation. So each of these is its own transformation. Right? There's 3 different things going on here. So without looking now, since we've done all these so far, what does this negative do in front? Reflect. And if you haven't kind of summarized in your head yet, the negatives are always reflections. It's just knowing what is it reflecting over. So we know that is going to be the x. This is going to be the y reflection. Got the y axis. And what is this 1/2 doing? What is that called? Vertical this time. Vertical dilation. And what is the factor? Just stays the same. What else we got going? This together is called the y-intercept. So much information all packed together. And this may be a little difficult without the parent function, because we don't even have the graph up here. We would start with 2 to the x. But really, we're starting with this function, 2 to the x, this original function, black, and doing all those things. We're going to reflect it on the x, reflect it on the y, and then go half the distance towards 0. Okay, so reflect, half the distance towards 0. That's what this all means. So we want to think about it a little bit. The y-intercept, well, they kind of give it to us, so that's going to be negative 1/2. So normally it's 1, but then it gets reflected across the y, which doesn't move, but then reflected across the x. Now it's at negative 1, and then you go half the distance. That's why it's at a half. And then we just repeat that process. So, or you could just plug in the numbers, but try to imagine plugging in 1. That would be at 1/3, which reflects to negative 1/3. Right? Oh, this is to the 2. Sorry, to the sec. Base of 2. So it starts at 1, 2. That's right here. And then reflects to here. And then reflects to here. And then goes half the distance. Ends up there. Okay? That's that process. Started here. Reflect. Half the distance. And we have to do that for the remaining. So we have usually we had 2 to the would be at 4. So we reflect over here, and then down to here, and then half the distance. And then 3, right? That'd be go start at 8, over here down to -8, half the distance, -4. And we could even do 4 because we're taking half of it. So usually 4 to the 4th is 16. Reflect over the y-axis, 16. Reflect down here to 16. Half the distance is -8. And we can sketch in our graph. There we go. Nice. All right. Lastly, without a graph at all. So can we get this information? Kind of like we just did here. We didn't graph it. We already knew this is what's going to happen. This is just in function notation. Right here. So we have, if you want to, you can, if you know how to do it, if it's connected to the x, that's going to be either horizontal translation or dilation, but since it's -3, we know that it's going to be the same as 4 to the x minus 3. So we have a horizontal translation to the to the right. Yeah. So we can say shift right 3 units. And if we have the number on the outside, right? So it's not connected to the x, so we know that's going to be a vertical, right? And since it's plus or minus, that is a shift 5 up, or translate 5 up, either way. It's up. Okay. Then we have to the -2x, which we did earlier. It's just 4 to the -2x. So there's two things, right? The negative and the 2 do two different things. Negative is -x and just 2x. So the negative, right, reflect y-axis, while the 2 horizontal dilation. What is the factor? 1/2. So half's the distance to that axis. All right, good. And one more. So we have -3 times 4 to the x plus 1 minus 2. So breaking it all down one more time. What does the negative do? What does the 3 do? What does the plus 1 do here? And what does the -2 do? So if you can answer all those without checking any other examples or the notes or anything, you're in good shape, because that's pretty much all the above. That's got a lot going on. Not vertical, reflection. X-axis, I got it right this time. Vertical dilation, factor of 3. And we have a horizontal shift 1 left. And then we have lastly, a vertical shift. Down 2. lots going on, but hopefully it's familiar. I mean, this is a lot of geometry, just applied to new exponential functions. All right? Okay, you guys got the homework, and you got a little bit of time, so get that done as much as you can. See you next time. Oh, yeah.